All right. Hello, everyone. Thank you for coming to our talk, Extreme Privilege Escalation on Windows 8 UEFI Systems. Thank you, thank you, thank you. Yeah, all right, let's break some stuff. This talk's going to be extreme, so prepare yourselves. All right, so who we are, we work for the MITRE Corporation. MITRE is essentially just a federally funded research development center. Not going to bore you guys with details, so let's continue. Here's the outline for today. We're going to talk about the agony of Ring 3. Yes, you already have Administrator Command Prompt in Windows 8, but it is not enough. There are new lands we can explore, more extreme places we can go. That's exactly what we're going to do. We're going to be talking about how we can get into these other areas, what they are, what we can do there. We'll be talking about some exploits that we use to break into these areas from Windows 8. We'll be talking about some agents we can embed into these other privileged, extreme areas to do our bidding. And then finally, we'll offer a defense for how you can detect if someone is attacking you at the EFI level. All right, so here we are. As a security researcher, we have arrived at an Administrator Command Prompt on Windows 8. Normally, most researchers would pop calc.exe at this point, say, awesome, I've won, give me my money for my bug bounty, and then that's it, presentation is over. But there are still limits to Ring 3. There are things that you cannot do. Even as an administrator, there are instructions you cannot execute, memory you cannot see, and so forth and so on. As attackers, we always want more power, more persistence, more stealth, and there are limits to what you can do in Ring 3, even as administrator, so we must escape beyond Ring 3 into other lands that are completely unbounded and let us do everything. Now, that was my introduction. Some of you are probably wondering, should I have stood in line for this talk? Should I have gone to the talk next door? Well, I'm going to tell you right away, you definitely should have come to this talk. You don't have to take it from me. You could take it from the authority figure Snare, who is a fellow security researcher. And he says that if you can reflash the firmware, that is 11 out of 10, so awesome, would buy again, and that is exactly what we're going to do in our presentation. So this presentation is 11 out of 10. I go ahead and tell you that. Don't believe me, believe Snare, so you definitely want to be here for this talk. Now, so generally what we're talking about here is post-exploitation privilege escalation. Like I said, generally once you have the Administrator Command Prompt in Windows 8 or whatever, you're in the post-exploitation phase, but there are other places that you might want to go to and security boundaries in the way of you getting to those other areas. For instance, the Windows kernel. On later versions of Windows, you can't just inject arbitrary code into the kernel because there's the authentic code, driver signing, only signed drivers can get into the kernel. Now there are, technically that's the case. There are some attacks against this where you can put arbitrary code into the kernel. This particular attack model has been explored by other researchers very well. Juru has an excellent series of articles on it. Joanna Rutkowska talked about loading a known vulnerable but signed driver and then exploiting it. So this has been well hashed out. We don't want to talk anything more about this. We want to explore other more extreme possibilities. So here are a few other options for what we can do in the post-exploitation phase. We can go from admin Ring 3 to bootkit the system. We can go from Ring 0 onto the platform firmware. Or we can jump into system management mode, which is a super privileged mode of execution on the x86 processor. Unfortunately, we live in a dark world today where we can't do any of these things, at least not trivially. We can't just bootkit the system because UEFI has secure boot and will prevent us from doing that. We can't write to the platform firmware because the firmware only accepts signed BIOS updates because there are flash protection mechanisms that your OEM is going to set to prevent a malicious actor from coming in and just writing arbitrarily to the BIOS. And then finally, we can't get into system management mode because not even Ring 0 can even read system management mode. Only SMM can read or write to SMM. It's protected by the memory controller hub, basically. Now, luckily for you, you're coming to this talk, and we're going to introduce the idea of extreme privilege escalation, which lets us go all the way from administrator, Ring 3, so admin command prompt Windows 8, to the platform firmware. Now, the important thing here is on this diagram, these privileged domains are ordered from on the y-axis. The higher you go, the more privileged you are, and anything more higher up on this diagram can clobber things lower on the diagram. So if you're in the platform firmware, you can get into SMM. If you could bootkit the system, you can get into Ring 0 and so forth and so on. You can always snake your way down this diagram. So once you can get to the platform firmware, you're free to take out all these other privileged domains. Yeah, what I just said. All right, so our target of attack for today is a Windows 8 system. Most Windows 8 systems today, pretty much all of them actually, will ship with UEFI firmware, which is essentially the replacement for a conventional BIOS. If your computer has the Windows 8 sticker on there, almost guaranteed you have UEFI on your system running underneath the operating system, helping you turn on your computer and so forth and so on. Now, this is the obligatory UEFI diagram that every BIOS researcher puts in their presentations, and essentially all you have to know about BIOS and the firmware is its job is to turn on the computer, initialize it, find the operating system, and just transfer control to the operating system. So turn on the computer, find the OS, transfer control to the OS. The other important thing about this diagram is that it's advantageous for us to break into the processor as early as possible, because as the boot up proceeds, the system becomes more and more locked down. There's more and more locks placed on the chipset, less things you can do, like the flash gets locked down, SMM gets locked down, so forth and so on. So the earlier we can break up into the boot up of the system, the better, because the system will be in basically a completely unlocked state, and we can do absolutely whatever we want if we can get in early enough. By the time the OS gets control, the devices, the firmware is like very locked down, and there's really not a lot you can do, even from ring 0 when we're talking about these other privileged domains. Now, Windows 8 has introduced a new special API called Set Firmware Environment Variable, which lets you set these, well, exactly what it says, firmware environment variables. Now, you can think about these as kind of like Unix, Linux type environment variables, like your path variable, your term variable, etc. UEFI has the same things. Generally, they look like the platform language, the boot order, and lots of other crazy things. There's all kinds of crazy environment variables in the firmware. And Windows 8 has introduced an API that allows a privileged, so admin ring 3 process to interact with many of these firmware variables. So essentially what this looks like is Windows 8 can call this API and just like set a variable to whatever. And then many of these variables will be automatically parsed by the UEFI firmware when UEFI has control. Now, when I went about thinking about, okay, I want to audit UEFI and try to find vulnerabilities in UEFI, immediately when I saw this environment variable API and UEFI variables, I started thinking about, this is a lot like Unix and Linux environment variable vulnerabilities back in the early 2000s. So some of you might recall that back in the day, you could do like set term equals 1,000,000 A's and then call some privileged application xterm or something like that, and it would try to parse one of those environment variables, and it would misparse it, and there'd be a buffer overflow, and you could escalate from non-root to root. So it was like privileged escalation in Linux. That's exactly the attack methodology I had in mind when I started looking at these UEFI variables. I thought, okay, there's lots of these variables, a lot of them are parsed by UEFI, and some of them have really complex contents with things like pointers, lots of arithmetic going on in the integers, and lots of weird proprietary things that we don't understand. And this is the type of thing where memory corruption vulnerabilities typically occur. So, okay, I like this. I definitely want to target this as an attacker. Now, we've already found some vulnerabilities in this variable interface. One we found in particular was the setup variable that we co-discovered with Intel that allowed bypassing of secure boot. But to be frank, this vulnerability was probably only like a 5 out of 10 on the awesomeness scale that I showed you in the beginning, the snare awesomeness scale, because it only lets you bypass secure boot. You couldn't reflash the firmware, you could brick the firmware, and it only affected a number of, like a subset of UEFI systems, only some OEMs and some IBVs, because it basically came down to a weird implementation mistake that some of these OEMs were using. So, okay, 5 out of 10, kind of cool, but we can do better. This is the BIOS development ecosystem, or at least an idealized view. We have UEFI, and Intel provides an open source UEFI reference implementation that's just like a bunch of open source code for how you should program UEFI firmware. Theoretically, you have these independent BIOS vendor entities like, oops, running out of power. Yep, so we have these IBVs, American Megatrends, Phoenix. You've probably heard their names, but they basically make BIOSes and sell them to Dell and HP for them to use on their own personal systems. So theoretically, American Megatrends, Phoenix will take the UEFI code, use it to develop their own like development kit, and then sell or license that development kit to Dell and HP. And Dell and HP will use those development kits to write their own firmware and their own BIOSes for their own systems that they ship and sell to you. All right, so the point is, if I can find a vulnerability in the UEFI open source reference implementation, theoretically it will like trickle down into all these other entities, and I'll have a very widespread vulnerability that affects all these other Windows 8 systems that are using UEFI. Okay, so auditing UEFI, like I said, it's open source, so it's relatively simple. You just got to check out the code and then go to town. Now, as attackers, we always want to zero in on, okay, I'm starting auditing this code, so what exactly is attacker-controlled data? Where are the boundaries between this more privileged piece of code interacts with attacker-controlled data? Well, as I already explained to you, one of these intersections is the UEFI variables. We know that Many of these are controllable by the operating system, so it's basically attacker-controlled data, and the firmware is going to automatically parse many of them when they're created. So this is the data boundary that we want to explore for vulnerabilities. Now, also last year at Black Hat, we presented an attack against a Dell BIOS update routine, where normally you can only update Dells with signed BIOSes, but we actually found a memory corruption vulnerability in the update routine that allowed us to hijack control in the context of the update routine and reflash the Dell computer with an arbitrary, malicious BIOS image. So we had this experience, and it just so happened that UEFI outlined a uniform capsule update mechanism for updating UEFI firmware. Now, this is not directly callable or Ring 3 code, so there is no interface accessible to Ring 3 code in Windows 8 that says start capsule update. However, we found that it could inadvertently be started by creating a special UEFI variable. And if this UEFI variable existed, UEFI would automatically start the capsule process. So even though it's not directly exposed, it is inadvertently exposed. Now, so what that means is that we have a very good intersection between this is what we wanted to look at, UEFI variables, and this is what we have past experience with, firmware updates. So capsule update, that's good. This is a good first target to attacking UEFI. So this is basically how capsule update works. You have a firmware capsule that contains things like a BIOS update. It can do other things, but for the sake of general discussion, let's say BIOS update. And the operating system will take this capsule and then scatter write it to memory in case the RAM is constrained and you can't find a large contiguous allocation. They'll just like scatter write it to the address space. And then the operating system creates a special UEFI variable called capsule update data. And it's essentially a pointer to a scatter gather list which links to the location of all these individual fragments for the capsule in memory. Now, whenever UEFI gains control, it's going to automatically look for the existence of this capsule update data variable, and if it exists, it's going to go about trying to coalesce this fragmented capsule that was in the address space back into its original form. So once it has the UEFI or the capsule coalesced, it's going to parse some of its envelopes that are encapsulating the capsule update and verify that it's been cryptographically verify that it's been signed by the OEM and so forth and so on, because you don't want to have the firmware just parsing unsigned capsules. It has to make sure this definitely originated from the OEM. This is OEM code. You're definitely not supposed to be able to reflash your BIOS with just arbitrary content, so you better verify that capsule as it's coming in. Once the verification passes, assuming it does, it will consume the actual contents of the capsule, so presumably firmware update, but there's also been proposals for running like malware detection independent of the OS, so it's a general capability, but in general you're going to see it for firmware updates. All right, so with that in mind, we knew what are opportunities for actually exploiting this capsule update process? Well, we know the vulnerabilities have to occur before the cryptographic verification. You know, once a signature check occurs, UEFI will know that this is a bogus capsule and it will not proceed, do not pass go, do not collect $200, so the vulnerabilities have to occur before that. Well, the coalescing phase, all of that happens before the signature check because the fragments are controlled by the operating system. The parsing of the capsule envelopes, many of the envelopes we found would be parsed by UEFI before the signature check actually occurred, so it had to parse many of these envelopes to actually facilitate the signature checking process. So any memory corruption vulnerabilities in these envelopes could be used to hijack control of the instruction pointer in the context of UEFI. And the third and final option was parsing of unsigned content within the capsule. Now, this was actually where the first BIOS vulnerability was found, at least the first one that we're aware of. In 2009, Invisible Things Labs found a BIOS reflash attack that it revolved around the unsigned splash screen on your system. So with this Intel BIOS, you could update your splash screen to have your company logo, you know, whatever company you're working for, MITRE, be displayed. And this was unsigned content embedded in the signed BIOS update. And in their case, they found that there were some memory corruption vulnerabilities in the parsing of that unsigned splash screen, and that allowed them to get control. So these are our three main attack vectors: the coalescing, the parsing of the envelopes, and the parsing of unsigned content within the capsule. Oops. Okay, so we audited the UEFI code, and guess what? You're here today, so we found lots of bugs, obviously. What's interesting is many of these bugs took the form of like, do not do this 101, and, you know, type unsafe languages. So integer overflow 101 type stuff like arithmetic before sanity checks and multiplication before allocation. If you're a veteran source code auditor, you know definitely do not do this. And if you are a veteran bug hunter, you would have zeroed in on these things and say, I think this is problematic. Like in this case, bug number, what I'm calling bug number 3, if numblock is really large, the multiplication will overflow and the allocation for LBA cache will be unexpectedly small. So these are actually quite obvious. Like I said, veterans in the audience will know that, yeah, I could have spotted these things quite easily. So we spent about a week looking. We found a number of bugs. We were able to chain several of them together to come up with 2 different exploits, what we call the Queen's Gambit and the King's Gambit. Zeno and I are both big nerds, obviously, because we like BIOS, and because we're nerds, we also like chess, so we started naming all of our exploits after chess openings, hence the Queen's Gambit and the King's Gambit. The Queen's Gambit occurs when what's known as the PEI phase, just a special part of UEFI boot, that is very early while the platform is completely unlocked, and the Queen's Gambit, where the King's Gambit occurs in what's known as the Dixie phase, so later on, but still early enough for most of the system to be unlocked. Yeah, using both of these exploits, we're able to reliably get control of the instruction pointer in the context of the UEFI and do nasty things and break into these other like privileged domains that normally even Ring 0 code cannot break into. Now the funny thing is, when I was auditing this code, like I said, many of the vulnerabilities were easy to spot, and in fact the developers were obviously aware that there were possibly like bad things that could be occurring. Like you see in this comment, it says more liabilities, checkup, will do later, and like should add additional sanity checks here, and so forth and so on. So, okay, whatever. Obviously there would be an issue, but they didn't actually bother to fix them. And just in general, the presence of these like really easy to find vulnerabilities and absolutely security critical code that is open source was pretty disturbing to me. And we're forced to conclude that, guess what? No one else is looking at the BIOS. Otherwise you guys would have found these vulnerabilities years ago, or maybe you have found them and you have 0 days and you're exploiting each other, in which case, whatever. But yeah, so other good, researchers aren't coming up here and like reporting these bugs to Intel or whatever. So yeah, okay, so these bugs are easy to spot. It's kind of weird, just interesting observation. Now, the bugs were easy to spot. However, exploitation was very complicated. This is despite the fact that that code I just showed you runs in an environment that is completely exploit mitigationless. It runs in flat protected mode with no paging, and essentially that means all code is readable, writable, executable. Everything is at predictable locations, so no modern mitigations whatsoever, even though it's in this, it's very security critical, but no mitigations. Despite all this, exploitation was still brutal and took me months and months and months to actually accomplish, even though it only took me a week to find the bugs. So at this point, in previous presentations, I've gone like line by line, the IDA files, memory map, blah, blah, blah. This is how I did X, Y, and Z and the ROP payload to exploit the vulnerability. And after 5 minutes of doing that, the audience was totally asleep. So I'm not going to do that to you guys today. Instead, I'm going to show you this crazy diagram and say, if you're a fellow vulnerability researcher and exploit developer, please read my white paper. I spent many, many days writing like a 20-page, fully detailed white paper that goes into all the gory details of how I exploited these vulnerabilities. So this is just to entice you to read the white paper if you like that sort of thing. The point being, with the Queen's Gambit exploit, we achieve a very reliable surgical write, what, where primitive, which is basically the holy grail in exploit development. The King's Gambit vulnerability was especially interesting, the one in what we call the Dixie phase, because essentially you end up in a situation where there's a non-terminating loop that's going to overwrite the whole 4 gigabyte address space with only partially influenced values, so you're just clobbering the whole address space with values you don't even completely control. How can we possibly escape? Well, the only way I could think of to actually exploit this was to like have the non-terminating loop overwrite its own code as it was executing. And so in this case, you can see that like, basically I wrote a crazy Python script to brute force all the ways I could instantiate this vulnerability. And in one of those instances, I found a case where I could instantiate it so that the non-terminating loop would self-override itself with a jump away to a non-corrupted part of the address space that the OS could control. So that you could just jump away into OS-controlled shellcode, and then we'd get our privilege escalation. This one isn't as good as the other one that I just showed you because it corrupts a whole lot of the address space, so it essentially destabilizes the system and limits what you can do after you get control of the instruction pointer. But it's still kind of interesting, so please read the white paper if you're interested in the details. Now, what else is interesting is that we're able to exploit the Queen's Gambit vulnerability using only that special Windows 8 UEFI variable API. So part of the exploitation process required me to stage certain things at certain physical addresses in the address space. Normally in Ring 3 you cannot do this. If paging is disabled and so forth, you won't have access to all of the physical address space to put things where you want. But I found that by further abusing the Windows 8 UEFI variable API, I could spray the contents of the flash chip with like a heap spray and just create many of these UEFI variables. And eventually, after I had created like a whole bunch of them, I would know that at a certain physical address, I would have attacker-controlled content. So just think heap spray using UEFI variables. Using that, I was able to exploit the first vulnerability that Queen's Gambit exploit using only the Windows 8 API, so I didn't have to rely on anything else. The second one, there were some constraints, and we had to like use the crutch of a third-party driver to put things at certain physical addresses. So. Yeah, in both cases, attacker ends up controlling the instruction pointer very early in the boot of the system where the platform is like completely unlocked, system management mode, the flash, etc. So you can do whatever. So, okay, what was Corey just saying? That was totally crazy. Some of you guys are like, I don't understand this attack model at all. So let me just sort of narrate it step by step what this would actually look like. We have our Dark Jedi, Sith attacker. Yes, he has an administrator command prompt, but no, for the Dark Jedi, that is never enough. He always seeks to grow his power to the next level. And he says, okay, that's great, I'm admin, but I must go further. I must explore other dimensions, get more knowledge, get more power. So first what he does, he says, I'm going to spray the contents of the flash chip with all these UEFI variables that contained shellcode and an evil capsule to instantiate the vulnerabilities. And he knows that after he's created a whole bunch of these, very reliably so, that he will have attacker-controlled data at physical address FFF91000, and he needs that for his exploit payload to work correctly. Then after he's finished his heap spray, variable spray type thing, he creates the evil capsule update data variable, which instantiates that standard capsule update process in UEFI, if it exists. And he points that within his sprayed area, basically the evil scatter-gather list to instantiate the vulnerabilities. And then this is where I'm going to wave my hands a little bit. A platform reset occurs. This actually is a bit implementation specific and depends on what hardware you're actually running on. In most cases, this is going to mean like S3 sleep, but it could mean other things depending on your hardware. So once the platform reset occurs, UEFI is going to regain control. You're going to be executing in the context of UEFI. It's going to check for the existence of this scatter-gather list, the capsule update data, and if it exists, it's going to automatically start parsing the contents of the list and trying to coalesce the capsule and so forth and so on. So in this case, the evil scatter-gather list that pointed to by capsule update data points inside the contents of the sprayed data that our evil Dark Jedi has put onto the flash chip using this variable interface. And in the process of parsing it, because of those vulnerabilities that I pointed out, the attacker gets control of the instruction pointer in the context of UEFI. Now, since we know there's no mitigations, no execute stack or whatever, the attacker can just pivot instruction pointer back to the contents of one of those sprayed variables, which contains some shellcode to do something. What that something is we'll talk about a little bit later. But in most cases, it'll be something like copy yourself into system management mode, which will be unlocked at this point, or reflash the flash chip, which normally you can't do, but in this case, the flash chip is unlocked, so you the attacker can overwrite the contents of the flash chip and embed some type of agent into the BIOS or into the firmware. So no physical presence needed. This can all happen as software just using that Windows 8 API. So what can they do? Why would the attacker be incentivized to go into these extreme new lands like system management mode and the platform firmware? Well, once you're in the platform firmware, you can completely brick the system by overriding the flash chip, so not even like trying to reinstall the OS will work. It won't even power on because your BIOS is dead. You can defeat secure boot because the secure boot code is stored on the flash chip. They can establish an undetectable SMM rootkit. Don't believe me? You should look at our CanSec West work where we talk exactly about developing an undetectable SMM rootkit. Or we also gave a talk at Black Hat last year, BIOS Chronomancy, about further developing an undetectable BIOS rootkit and so forth and so on. You can subvert hypervisors because the BIOS is below the hypervisor and can interfere with the hypervisor, even the TXT late launched hypervisor, because you don't have an SMM transfer monitor. You probably don't anyway. And then, yeah, once you're in these lands, you can pretty much do anything. Anything the CPU can do, you can basically do at this point. There are no constraints to your power. All right. So, normally, Zeno and I like to do video demos because video demos are safer. Today, for you, special audience, we have tried to create a live demo of one of these BIOS exploits. Thank you, thank you. Don't clap yet. It might not work, it might not work. 50-50, okay? 50-50. So, yeah, it's 50-50. We're doing it on one of these development boards, and these development boards are sort of like kind of finicky sometimes. Windows 8 isn't really designed to run on them. We just like hacked Windows 8 to run on it, just so we could exploit the underlying UEFI code. So maybe it'll work, maybe it won't. Cross your fingers, pray to Papa Legba. You see him in the background there. He's like the god of Haitian voodoo, the gatekeeper between the spirit world and the real world. So we're going to call upon Papa Legba. Papa Legba, hear my call, make our demo work. So let's give it a go. Okay, before you shut down Zeno, First, you can see this output here. It's using the Windows 8 UEFI variable API to create all these variables. You see like variable spray 0, variable spray 1. This just contains the evil capsule as well as the shell code. And he's spraying it all over the flash chip so he gets the attacker-controlled data in a predictable physical address. You see an error eventually, and that's just because the flash chip runs out of room to store variables, so it says, I can't create any more huge variables for you, Corey. Sorry, you're just going to have to work with what you got. And it also creates the evil capsule update data variable to point inside the contents of these sprayed flash variables. All right, so go ahead and reset. Okay, so one other thing I have to say is that we're going to have to boot into the EFI shell to put the system into S3 sleep because Windows 8 doesn't know how to put these systems into S3 sleep. Normally from administrator command prompt in Windows 8, you can put the platform into S3 sleep, but on the Minnow board we can't because there aren't the right drivers for the Minnow board. So we're just going to boot into the EFI shell to put into S3 sleep to actually engage the vulnerability.
All right, so if we can't see that on there, we'll have to tab over here.
Okay. Yeah.
We'll just talk to it right here. Talk to it.
Oh, yeah, but they're not seeing it on the projector. Yeah, just give us 1 second. AV issues. Okay, so yeah, back to Windows 8. This is the EFI shell just over a serial terminal here. And Zeno's just going to put it, well, first, are you going to do the find spray first?
Yep. Okay.
So we're going to call something that's basically going to tell us is the exploit going to work or not, or at least give us some evidence. We see hit spray location FFF940C2. That's good because that's the address I hard-coded into my exploit. I assume this would be the reliable address if we did the flash spray technique. So everything seems to be going so far. Here is another place where the demo can go wrong. We're going to try to put the Minnow board into S3 sleep. Even from the EFI shell, sometimes this is finicky. Sometimes it will not go into S3 sleep and it'll just hang here. It takes like sometimes 30 seconds. So let's all sit here and hopefully Papa Leg Bell will be merciful to us. Otherwise we'll just try to like manually reset the system.
Think about what you can give a preview of the fact that we're going to be installing.
Okay, so right, as if the system boots up, if the demo works, it will hit the shellcode, and essentially what we're going to be doing is making writes to the flash chip that will embed an agent in system management mode to do our bidding, and it's sort of like a backdoor methodology that Zeno will talk about more. We'll talk more about what it's supposed to do and how it works, but we'll see. You want to just hard cycle it at this point? Okay, so it wasn't going into S3 sleep. Sometimes we just have to reboot it and try again. Luckily, the exploit payload is still waiting there in the variable contents for UEFI to parse. And then if we can get it to go into S3 sleep, then the exploit will hopefully work. If it works, you'll see it say something like running from spy flash. That's how we know that it's actually running from S3 sleep. Oh, there we go. There we go, finally. Okay, so at this point, it has gone into S3 sleep and woke up with an immediate wake, and it started to parse our evil capsule. So at this point, we've actually been corrupting the firmware on the flash chip, which we're definitely not supposed to do. And Zeno's actually going to hook up this EEPROM programmer just to show you the writes we made to the flash chip, which just to emphasize, normally you can't do this.
You can keep talking.
So yeah, normally to inspect the flash chip you need this like special EEPROM programmer we have here is called the DEDIPROG, and it's just going to manually read the contents of the spy flash chip. So if you have physical access, yes, you could overwrite the flash chip. You could just come and connect something like this to it. But the important thing is we're actually making the modifications to the flash chip with software-only methods, so we could do this without ever having physical access to the system. So Zeno's just going to the point where we would have embedded the agent at this point.
So that's it, but I can't scroll forward.
Okay, yeah, so you can see where it turned red. That's basically, we identified a padding area on the flash chip for this development board, and we just injected one of our agents there that will eventually copy itself into system management mode. So that's just one of our writes. Everyone should be impressed, because normally you can't do that. Oh, we just wrote to the flash chip using software-only methods. Yeah, thank you, thank you, thank you. So, everyone's totally unimpressed. You just clap because I told you to. Well, Zeno's going to show you what this agent actually does and how we can interact with it and why it's cool and so forth and so on. No, how did we end up with that? Okay, so now I'll switch it over to Zeno.
All right. So, behold the first appearance of the watcher. So we just showed that we injected an agent into the flash chip. That's going to persist. It's going to always exist down at the flash level. It's going to run every time you boot the system, and it can, do sort of anything. So, looks like we lost a slide here. But basically, the point is we get asked the question, right, consequences. What does it matter if you break into BIOS? Who cares if people attack firmware, right? And so the basic point is we always say, okay, what can an attacker do? They can do everything, every single thing. If there's an attack, they can do it, because this is the most privileged code on the system. There's nothing it can't do. And it turns out it also is sitting there down at the lowest level, running before all operating systems. So if you can boot my Linux here. So we just did the exploit from Windows. We're now going to boot it into Linux instead, because we want to show this agent down at the firmware level is persisting and running and continuing down below the system, and it doesn't really care who actually is up there at the operating system. So at least the one that we made didn't. So what is the watcher? It is it's an agent which is sort of minimally simple. It's like the simplest possible thing you could make if you wanted to make a backdoor, but it's maximally capable, because all it does is it scans memory and it tries to find special signatures in memory. And when it finds a signature in memory, it then treats what's after the signature as assembly that it should run, right? So it just jumps into that assembly that's after the signature. And that means we don't need to build in every capability in the world to the watcher. We just need to have it continuously waiting and watching and scanning your memory. And it doesn't really care how a payload gets into your memory. That payload, use your imagination. Someone shoots some packets at you and your thing may say, oh, nope, I have my firewall on, I'm going to drop those packets and not process them. But it doesn't matter, because they got into memory, and the watcher is sitting here waiting and watching and reading memory and looking for signatures. So a whole bunch of different ways. The command and control, again, maximally flexible, because basically anything that gets into memory anyway, the watcher can find it, the watcher can execute it. Right, so I'll just speak a little bit about what we did in terms of design trade-offs. Right, so it's scanning memory. Well, you don't want to scan all of memory. That's going to take too long. So we want to scan on page boundaries every hex 1000 chunk of memory. And so watcher is just sitting here running in the background, scanning every hex 1000 chunk of memory for magic signatures. And so the controller somehow positions data into your memory, right? It doesn't matter how. You opened a document that had a payload attached. They man-in-the-middled your web page, and some JavaScript sprayed some payload into your memory. But basically, somehow, some way, the controller gets content into your memory, and then the watcher comes along and finds it and starts executing an arbitrary payload that can do anything. So we will show some simple, the watcher, an important point is the watcher was pretty much an afterthought to this presentation. The Corey stuff and the attacks on UEFI, that's the meat of the presentation. The watcher was just, people don't get it that when we say, if you break into firmware, you win everything, okay? So we needed to make this clear, because some people only get it when you make it, perfectly clear. So we're going to show a simple demo. In the comic books, the watcher is from an alien race which is forbidden to interfere, but yet he always somehow finds a justification to interfere anyways and warn us about attackers and so forth. But all right, so in this case, what we're getting, you can see here, we booted into Angstrom Linux. That's the Linux that happens to come with the Minnow board. And so to sort of prove that the watcher is sitting here waiting and watching in the background, what I'm going to do is I'm going to manually invoke an SMI, a system management interrupt. We could have it running continuously, always in the background. We just ran out of time for doing demos. Like I said, it's an afterthought. But we're going to manually invoke an SMI, and we'll prove that there's someone hidden in the background who's actually executing code. Right, and the key point is, we're still on the same system. We booted into Linux. This is still the same development system that we were booting, hard drive with Windows, little flash chip with Linux. Same system. The watcher is sitting there underneath. It can subvert any operating system, any hypervisor. It really doesn't care. So what I'm going to do is I made a little UEFI, this is a Linux application, and what it does is it just writes to a port in order to cause port I/O that causes system management interrupt, and it wakes up the watcher and it says, hey watcher, go scan memory right now. So if I pass argument 8, I am sort of waking up the watcher, and he's not finding anything because I'm not staging a payload, I'm not creating magic signatures for him to find. But if I do IO9, then what I will see is he will find this payload and he will execute you can think of it as shell code if you want, right? And there we go. So the watcher has infected the system, and he's waiting, and he's watching, and he's executing things. So the watcher itself, printed out watcher, though I'm forbidden to interfere, maybe just this once. The payload, okay. The payload for this particular example, again, just to make it blindingly clear, the payload for this, it could do any sort of shellcode that I want, but what it did in this case is the watcher passed it the address of a print function, a serial print function, and so the little bit of assembly, all it did was it took and it, passed the arguments into the print function and then passed a pointer to the string, and then the string prints out, right? So that's an example of the watcher just sitting around and waiting and executing things. So now we're going to try like our 50-50 probability, maybe it'll work, maybe it won't kind of thing. We wanted to make it clear it doesn't matter how stuff gets into memory. Here I just ran an application. The application, created a special buffer with a special signature and then some assembly after the signature to execute. I'm going to now try, and I'm going to try to send some ping packets that have watcher payloads and watcher signatures and watcher shellcode in. And specifically, the ping packets that I'm going to send, let's talk about the payload here. The payload we want to use here is the ultimate nullifier. So going with the comic book references in the Fantastic Four comic books, the ultimate nullifier was a device which is sort of extremely powerful. It could destroy universes, and it supposedly destroys only objects completely understood by potential user and destroys the user as well. So it's kind of the weapon of last resort. So the ultimate nullifier in our world is a brick the system sort of payload, right? So I'm going to nullify the first instruction that the CPU ever pulls out of the flash chip. And that means if the first instruction is junk, then you can't boot the system. You can't reboot the system into some USB drive and re-image the system. The first instruction the CPU ever executes is garbage. It's going to not boot ever again unless you have, unless you can go physically attach a flash chip rewriter. That's, again, part of the reason why we're using this demo board is because, we can easily reflash it, fix things as we're working on demos and so forth. You can't easily fix things on your personal laptops. So ultimate nullifier sent over the network in ping packets. Maybe it'll work, maybe it won't. We've been seeing that the network stack here is not so great, but Corey, if you'd... just you talk while I set it up.
Okay, so I just want to reemphasize one thing that we're having to do is you see Zeno did like the IO8, IO8, IO9. So normally we could program the watcher here to be periodically executing in the background by causing the chip to periodically generate SMIs. Totally doable. We unfortunately didn't have time to implement that, so every time Zeno does the IO8, IO9, that's just us manually having to do it, where when we go back and make this some more like weaponized proof of concept type of thing, it will just auto-magically go and find these payloads.
What the hell? Oh, not gateway broadcast.
So yeah, we're just bringing up a little local network, and then Zeno will have his MacBook, and you won't be able to see it, but it'll basically just be sending a ping packets to the development board. And embedded in the packet, we're using Escapee to generate these raw packets, will be a payload for the watcher, and that payload for the watcher is going to be brick the system. So the idea here is that some other foreign enemy state has broken into all of your computers and installed this watcher actor that's just waiting for the kill switch. Then finally, when hostilities break out, they're going to say, all right, country X, we're going to go and brick all your systems right before we launch an attack on you, because that's totally going to set you back way bad. So at this point, it's not sending the packets again. So.
It started up again. Let's go. Oops.
Okay, so we're going to try to see if it's going to work.
All right. Good enough.
Keep trying. I'm feeling optimistic. Is the IP address correct? Yeah, it's all these minor issues that end up totally screwing up our stuff.
IP is 10.0.0.1. Although we can't ping back that way. All right. Give it one more try.
Yeah, there's part of the issue is living in SMM and trying to intercept these packets is causing crazy packet loss. Okay, so
Unfortunately, we didn't get it to work remotely this time. It did work the last time, so 50-50, and our expectations were met. But we're going to run the payload. We'll just run it locally from the system, get the watcher to invoke it that way.
So we're actually going to run it as an EFI application now. So that last payload we... damn it, don't boot Linux. I want... no, it'll be fine. So we actually want to run it just sort of in an EFI shell. These are sort of EFI applications. They can, call into the APIs that are made available by the BIOS. So we did one payload from Linux. We're now going to do it from an EFI shell, and this is just going to manually nullify it. And then we'll sort of read the flash chip and show that we've actually bricked it. All right, so that was running the nullifier. It's the kind of thing where it's not visible, right? The important thing is if I pull this power out and I put the power back in again, you're not going to see anything on the screen because this thing is now bricked. Okay, there's no way for it to ever boot ever again unless I, come in here with the programmer and attach it and so forth. So we'll just show that like the bytes at the reset vector have actually been turned to zeros and nullified. Yeah. At Black Hat, I accidentally wrote to the chip instead of read to the chip, so we're going to try to not do that this time. So the reset vector for Intel CPUs is always at FFFFFF0, like 32-bit sort of FFF0. That's not right. Oh, I'm missing an F. So the reset vector on Intel CPUs is always FFFF0, right? And the way the hardware does is it takes the flash chip and it aligns the flash chip with the end of the physical address space. And so what we see right here is that the original entry vector would have been no op, jump backwards. And the ultimate nullifier has now just written 4 bytes of data, set it as 0000. There's no valid instruction. It can never jump back to the rest of the assembly. And it is now nullified, dead, bricked. And there's, on consumer systems, there's pretty much nothing you can do about it. Corey's telling me that I was actually running the wrong version of the Python script over here, so whatever. Okay, so we don't really have a lot of time, but you can go read these slides later. The main point is the watcher, as I said, it was an afterthought. It took a couple of weeks to build. It's minimally simple. You just have a tiny little thing which finds and executes stuff, and then it just, maximally complex in terms of what it can actually do. It can execute arbitrary shellcode. The watcher of tomorrow can have many different improved capabilities. But the question is, what can you actually do about this? Can anyone stop attacks like the Watcher? And the answer is yes. Yes, Copernicus can deal with the Watcher. So Copernicus is our defensive tool that we put out last year, and we've been improving ever since. It's basically a system that it does 2 things. It tells you whether or not your BIOS is vulnerable to attacks like the exploits that we were talking about, but more importantly, a lot of vendors just don't configure the BIOS correctly, and so the flash chip is just straight open. So that means anyone can nullify you at any point if they get, kernel privileges, and that's sort of a bad thing, and that's why we're trying to raise awareness of that with Copernicus. Intel has another tool, ChipSec. It also tries to tell people about that. But so we do both integrity checking and vulnerability checking. So Copernicus can dump your BIOS, and then you can go inspect. Have there been modifications that you don't expect? And if I had more time, I'd show you an example of the different ways we can install Watcher and the different ways Copernicus checks it. So I'm just going to blow through this quickly. The vulnerability disclosure, we actually told Intel about these bugs back more than 6 months ago. We have sort of a 6-month vulnerability disclosure timeline. And read the slides if you want to know more. But the one important thing here is that we did show this on a single HP system, like to prove that it was actually vulnerable. We showed that these UEFI things do trickle down into real systems. And as of yesterday, HP went live with their advisory saying that, okay, there's more than 500 different models of HP which are all vulnerable to these exploitable vulnerabilities. So go check that out. You're almost certainly vulnerable. So in conclusion, we talked about 3 things today. We've talked about a whole bunch of other things at other conferences. We're going to talk about some more stuff in the future. There's a whole bunch of other people doing a bunch of talks about other things. There's going to be a BIOS summary talk tomorrow. You should check that out at noon. And you'll find out more about all the different ways that you're hosed down at the BIOS level. So with that, we're out of time. We'll be outside, probably back that direction, taking questions. Thanks for your time.